If you walk into pretty much any major museum with an antiquities collection, you'll eventually find yourself staring at an ancient statue.
Right.
Let's say it's Egyptian from the Ptolemaic period. It's static, it's just stone or wood. But if you actually read the texts from that era, like the writings of Hermes Trismegistus, you realize something crazy.
Oh, yeah, the way they viewed them.
Exactly. To the people who built them, these weren't just representations or art. They genuinely believed these sacred mechanical statues possessed sensus and spiritus.
Actual feeling and spirit.
Right. They believed that by discovering the true nature of the gods, humanity could actually forge a reflection of that divine intelligence and sort of lock it inside a physical vessel.
It's really the ultimate act of human ambition, isn't it? I mean, long before we understood electricity, let alone microprocessors, we were just totally obsessed with breathing life into the inanimate.
We really were.
You see the exact same impulse in Greek mythology, with Hephaestus forging those golden mechanical handmaidens that supposedly possessed knowledge and could speak. Or Pygmalion carving Galatea. We have been trying to build a mind for thousands of years.
And sitting here today, staring at the exponential curve of modern technology, it feels like we are the generation that is finally going to watch that mind wake up.
Yeah, we really are.
So welcome to this deep dive. Today's mission is massive. We are pulling together an enormous stack of sources for you. We've got historical timelines from the 17th century, Alan Turing's original 1950 philosophical papers, deeply technical reviews of modern medical AI.
The new Epoch AI reports too.
Yes, the reports on compute scaling and even cutting-edge treatises on machine consciousness. We are going to trace the entire journey of artificial intelligence.
But, this isn't just some dry historical retrospective. This is a story that's completely defined by hubristic promises, crushing winters of academic disillusionment, and then these staggering, world-altering breakthroughs.
Total roller coaster.
Exactly. Our goal today isn't just to look at what AI is.
Yeah.
We want to tear off the casing and look at the underlying math and philosophy. We need to understand the mechanics of how it's doing what it's doing, how it's quietly rewriting the infrastructure of your reality, and ultimately what the creation of a synthetic mind reveals about the blind spots in human cognition.
Okay, let's unpack this, because you can't just jump straight into neural networks and ChatGPT.
No, definitely not.
To understand how we are building synthetic minds today, we first have to understand how we historically define the concept of thinking as a mechanical process in the first place. You really have to go back to the 17th century.
Right, because we had to fundamentally reduce the definition of human reasoning before we could ever even attempt to engineer it.
Exactly. And that reduction begins with Thomas Hobbes in 1641. In Leviathan, Hobbes essentially stripped all the mysticism away from thought. He proposed this radically mechanistic view of cognition, famously stating that, and this is a quote, "reasoning is but reckoning."
Which is such a powerful phrase, because he basically meant calculating.
Right, adding and subtracting concepts like numbers on an abacus.
Yeah, and that laid the philosophical groundwork for Gottfried Wilhelm Leibniz a few decades later, around 1679. Leibniz looked at Hobbes's idea and envisioned a literal universal calculus of reasoning.
What did he mean by that?
Well, his theory was that every single object, and more importantly, every abstract concept in human thought, could be assigned a specific numerical value.
So mapping the whole world to numbers.
Exactly. If you map the entire human conceptual universe to numbers, Leibniz argued, you could resolve complex human arguments through pure algebraic calculation.
Wow.
It was the absolute genesis of binary logic and symbolic AI, the idea that truth itself could just be calculated.
So the philosophers sketched the blueprint, right? The brain is a meat calculator. But the actual physical manifestation of programmable logic, the hardware, doesn't actually come from philosophers.
No, it comes from somewhere completely different.
It comes from the textile industry. This is where Joseph Marie Jacquard changes the world in 1804. He invents a mechanical loom that weaves these incredibly complex patterns. But the weaver isn't controlling the threads.
Right. The machine reads skiff caseboard cards with holes punched into them.
Yeah. It's the physical separation of hardware and software. The loom is the hardware. The punched cards are the software.
You swap the cards, you run a completely different program without rebuilding the loom. It's brilliant.
And that leads directly to Charles Babbage in the 19th century. He was designing his analytical engine to use those exact same punched cards to run mathematical calculations.
But Babbage, for all his genius, he had a pretty narrow vision. He just wanted a flawless calculator to print mathematical tables.
Right.
It was actually his collaborator, Ada Lovelace, who looked at the analytical engine and realized It wasn't just a calculator. She wrote that if you could convert musical notes or letters or formal logic into numbers, the machine could manipulate any data governed by rules.
She saw the big picture.
She totally did. Lovelace articulated the functionalist view of intelligence over a century before it even had a name. It's this profound realization that computation is substrate independent.
Substrate independent, meaning it doesn't matter what it's built out of.
Exactly. If the logic holds, it doesn't matter if the machine is made of brass cogs, silicon wafers, or biological neurons. Information processing is a universal property.
That conceptual leap really sets the stage for the 20th century. Theoretical philosophy collides with modern mathematics, and we get the true inflection point of this entire journey. Alan Turing.
Turing, yeah. He and Kurt Gödel had already spent the 1930s probing the absolute limits of formal logic, with Turing conceptualizing the universal Turing machine. But his defining intervention for our purposes happens in 1950, with a paper titled simply Computing Machinery and Intelligence.
I love reading this original paper because Turing is just so ruthlessly pragmatic. He starts with the question, can machines think? And then instantly throws it out.
Right, he realizes it's a trap.
Exactly. He knows that trying to define the words machine and think is just a metaphysical swamp. You'll argue forever. So he replaces it with an empirical behavioral test, the imitation game.
And the beauty of the imitation game, what we now call the Turing test, is that it bypasses the internal mechanics entirely.
How so?
Well, Turing sets up this scenario. An interrogator communicates with a machine and a human via a text-based terminal. The interrogator's job is to figure out which is the machine. Turing argues that if the machine can consistently deceive the human interrogator into believing it's human, then it is functionally exhibiting intelligent behavior.
He essentially declares that performance is the only metric that matters. If it walks like a duck and types like a duck, it's a thinking duck.
Pretty much.
But looking at this critically, and I think a lot of our listeners might wonder, this isn't passing a text-based chat test, just a parlor trick. I mean, fooling a human doesn't mean the machine possesses actual cognition.
That's a very fair point.
Because humans are incredibly susceptible to anthropomorphism, right? We project consciousness onto everything, from our pets to our cars.
You're hitting on the exact resistance Turing anticipated. A significant portion of that 1950 paper is Turing systematically dismantling what he called the 9 common objections. He knew people would recoil from the idea of machine intelligence, mostly out of, well, biological chauvinism.
He addresses the argument from consciousness, right? This was Professor Jeffrey Jefferson's critique.
Yes.
The idea that a machine has to actually feel emotions to write a sonnet or a concerto. Without subjective conscious experience, it's just a dead mechanism mimicking life.
And Turing's counter to Jefferson is basically a masterclass in philosophical jujitsu.
Yeah.
He points out that demanding proof of a machine's internal feelings ultimately leads to solipsism.
Because you can't prove anyone else feels anything.
Exactly. How do you, mathematically or philosophically, prove that I am conscious? You can't. The only way to definitively know that another entity thinks or feels is to literally be that entity.
And since we can't do that, we rely on a polite social convention. We observe each other acting as if we are conscious, and we grant each other the benefit of the doubt.
Precisely. Turing argued that if a machine behaves with the nuance, adaptability, and complexity of a conscious human being, demanding that it prove its internal emotional state is an impossible standard, because we don't even hold other humans to that standard. We judge each other purely on observable behavior.
He also goes after the head in the sand objection, which I find hilarious because it isn't even a scientific argument.
Not at all.
It's just this existential panic that if machines can think, human beings are no longer the apex of creation. The consequences are too dreadful, therefore it must be impossible. Turing just brushes it off as a fallacy of appealing to consequences.
Yeah, he really laid down a philosophical gauntlet. He shifted the entire scientific community from asking, what is the nature of thought, to, can we engineer a system that performs intelligently? But, of course, philosophy is easy compared to engineering.
Oh, absolutely.
Transitioning from Turing's theoretical framework into a dedicated scientific field required a monumental organizational push.
Which brings us to the summer of 1956, the Dartmouth Workshop. This is the moment the field names itself, and ironically, it's the moment it plants the seeds for its own near destruction.
The Dartmouth Workshop is basically the constitutional convention of AI. You have John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon gathering to dedicate 2 entire months to solving machine intelligence.
Just 2 months.
Right. And McCarthy specifically coins the term artificial intelligence to distinguish their work from cybernetics. Cybernetics was focused on analog, continuous feedback loops like a thermostat regulating temperature. McCarthy wanted to focus on digital symbolic logic.
The hubris in their original funding proposal is breathtaking to read today. They wrote, and again I'm quoting here, "The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it."
They really thought they had it.
They genuinely believed they could crack human-level intelligence in a single summer with a handful of mathematicians.
To be fair, though, the immediate aftermath justified some of that optimism. Look at the logic theorist, built by Alan Newell and Herbert Simon. It didn't just crunch numbers, it proved complex mathematical theorems. It even found a more elegant proof for a theorem in Whitehead and Russell's Principia Mathematica than the original authors themselves had found.
That is wild. And then a few years later, in 1965, Joseph Weizenbaum at MIT creates ELIZA, which is basically the world's first chatbot.
Oh, Eliza!
It mimicked a Rogerian psychotherapist by using simple pattern matching to turn user statements into questions. If you typed, "I am unhappy," ELIZA would just look for the keyword unhappy and output, "Why do you think you are unhappy?"
And Weizenbaum was famously horrified by the result.
Really? Why?
Because his own secretary, who knew perfectly well it was just a few lines of code, actually asked him to leave the room so she could pour her deepest emotional trauma into the terminal.
Wow.
Yeah. The Eliza effect proved Turing right. In one sense, humans are incredibly eager to project empathy and intelligence onto machines.
So the media and government agencies like DARPA, they saw these toy programs and basically extrapolated a straight line to utopia. They poured massive funding into symbolic AI, but that straight line was a total illusion. The top-down symbolic logic approach hit a catastrophic mathematical wall.
The combinatorial explosion.
Right.
This is the exact mechanism that triggered the first AI winter between 1974 and 1980.
Let's break down the combinatorial explosion for the listener, because it's a brilliant illustration of why human common sense is so remarkably hard to code. Symbolic AI worked flawlessly in what they called micro-world. Think of a chessboard. The rules are absolute, the environment is closed, the variables are finite.
Exactly.
But the real world is an open system. If you try to write if-then logical rules for driving a car down a busy city street, the number of intersecting variables just multiplies exponentially.
Because you're trying to calculate the trajectory of a pedestrian, the velocity of a bicycle, the changing traffic light, the weather conditions, all at once.
And the hardware just couldn't handle it.
No, the computational resources required to evaluate all those possibilities branch out so fast that they completely choke the hardware. The machines of the 1970s literally paralyzed themselves trying to calculate every possible outcome of just moving a robotic arm across a messy desk.
And this failure becomes super public with two major government audits. The ALPAC report in the U.S. absolutely devastated the machine translation community. It pointed out that after millions of dollars in funding, AI translations of Russian were actually worse than a human beginner's.
Ouch.
Yeah. And simultaneously, you have the Lighthill report in the UK exposing that AI researchers were fundamentally failing to scale their toy models into any real-world applications. The funding literally vanished overnight.
And that's the first winter. But the community eventually regroups in the 1980s. And they do it by completely abandoning the dream of general reasoning machines. They pivot to something highly specific: expert systems.
The architecture of an expert system is really fascinating. Instead of trying to build a machine that can think about anything, you build a machine that knows everything about one very narrow thing.
Right.
So you interview the world's top infectious disease doctors, and you manually hard-code their exact decision-making tree into tens of thousands of interlocking if-then rules.
And corporations saw immediate commercial value in this. They spent billions. Entire companies were formed just to build specialized hardware, like LISP machines, solely to process these massive rule-based databases.
But expert systems had a fatal flaw: brittleness. I always think of an expert system like a magnificent, sprawling library containing all the knowledge in the world, but there's no librarian, and all the books are super glued to the shelves.
That's a great analogy.
If you walk in and ask a question perfectly aligned with how the rules were written, you get a genius answer. But if you use a synonym, or if a patient presents with just one variable the programmers didn't explicitly write a rule for, the system doesn't degrade gracefully. It doesn't guess or improvise. It shatters. It just throws an error and crashes.
Because they lacked any semblance of foundational common sense. Plus, the maintenance was an absolute nightmare. The moment medical knowledge updated, You had to pay software engineers to manually unspool thousands of lines of code just to update a single rule without breaking the rest of the entire tree.
Right, which is
Right.
completely unsustainable,
Exactly. The economics collapsed, triggering the second AI winter in the late 80s and 90s.
which led to the knowledge diaspora. The term artificial intelligence actually became so radioactive that researchers rebranded themselves as data scientists or informaticians just to secure grants. The whole field scattered.
If we connect this to the bigger picture, it's a crucial lesson for our current era. It's the gap of reality. AI winters occur not because the underlying math is entirely flawed, but because the public hype drastically outpaces the hardware constraints and algorithmic limitations of the time.
So the top-down approach of hard-coding human logic failed twice. To break out of the 90s slump, researchers realized they had to abandon the idea of writing explicit rules entirely. If you can't build a mind from the top down, you have to grow it from the bottom up.
You have to mimic the biological architecture of the brain itself.
Exactly. This is the connectionist renaissance.
Connectionism shifts the paradigm to artificial neural networks, or ANNs. Instead of writing lines of explicit code, you create layers of interconnected nodes, modeled very abstractly on biological neurons. You have an input layer where raw data enters, an output layer for the prediction, and several hidden layers in between.
And the magic is really in the connections between these nodes, which act like biological synapses. Each connection has a numerical weight assigned to it, determining how much influence a signal from one node has on the next.
Yes.
But here's the critical part for the listener to grasp. Nobody is programming the network to know what a cat looks like. The network has to learn it autonomously through a mathematical feedback loop called backpropagation.
Backpropagation is the engine of modern AI. Let's say the network first makes a guess, predicting an image as a dog when it's actually a cat. It's wrong. The algorithm calculates the magnitude of that error.
I always think of backpropagation like tuning an audio mixer that has a million different dials. You
Right.
play a track and it sounds chaotic and terrible. A mathematical algorithm analyzes exactly how far off the pitch and rhythm are from the target song.
Right.
Then it works backward from the output speakers through the entire massive board, infinitesimally turning every single one of those million dials a fraction of a millimeter. It does this over and over millions of times until the static slowly resolves into perfect music.
That is exactly what the network is doing with its weights. It calculates the gradient of the error and adjusts the weights backward through the hidden layers to minimize that error on the next pass. The network slowly organizes its own internal structure to recognize complex patterns.
But because it's organizing itself based purely on statistical correlation to reduce error, it has absolutely no actual comprehension of what it's looking at.
Not at all.
The famous tank anecdote from our sources perfectly illustrates this alien intelligence. So the military trained an early neural network to identify camouflage tanks in forests. They fed it thousands of photos, half empty forests, half hidden tanks. The network trained itself and achieved 100% accuracy in the lab.
But then they deployed it in the field. They fed it new images, and its accuracy plummeted to random chance. It was totally broken.
Right. And when the researchers audited the training data, the catastrophic realization hit. All the photos of the hidden tanks happened to be taken on a cloudy day. All the photos of the empty forests were taken on a bright sunny day.
The network never learned what a tank was.
Right.
It didn't learn geometry or camouflage. It just found the easiest mathematical path to reduce its error rate, which was looking at the overall brightness of the pixels. It learned to distinguish between cloudy and sunny days.
It's incredibly powerful and simultaneously completely brainless.
Now, during this whole gestation period of neural networks, the symbolic approach actually had one final spectacular gasp. In 1997, IBM's Deep Blue defeated the reigning world chess champion, Garry Kasparov.
Oh, man. The media went wild. They declared it the dawn of thinking machines.
But
Deep Blue wasn't a neural network, right? It wasn't learning anything.
no, Deep Blue was the absolute zenith of the old paradigm. It was a massive, custom-built supercomputer executing purely brute force calculation.
Just evaluating moves.
Exactly. It evaluated 200 million chess positions per second. It didn't understand chess strategy. It simply calculated every possible branching consequence of every legal move deeper into the future than a human brain physically could. It was a triumph of parallel processing hardware, not a breakthrough in cognitive architecture.
So to see the actual big bang of modern AI, we have to jump forward to 2012. This is when deep learning finally works. And it only worked because of a completely serendipitous collision of three things better: neural network math, the explosion of training data from the internet, and a massive hardware leap courtesy of the video game industry.
I know it sounds crazy, but the role of the gaming industry cannot be overstated here. For decades, training deep neural networks with many hidden layers was practically impossible because of the vanishing gradient problem.
That's the vanishing gradient.
Well, as backpropagation tried to adjust weights backward through too many layers, the error signal became so infinitesimally small that the early layers never learned anything. They just stalled out.
Ah, I see. So this is where NVIDIA and the gaming industry accidentally save AI. For years, they had been building GPUs, graphics processing units, to render complex 3D environments in video games. The parallel processing required to render millions of polygons on a screen simultaneously happens to be the exact same matrix multiplication math needed to adjust millions of weights in a neural network.
Yes. When NVIDIA released the CUDA architecture, it allowed AI researchers to program those GPUs directly for non-graphics computation. They solved the vanishing gradient mathematically, and suddenly, a model that used to take 6 months to train on a standard CPU could be trained in a week on a cluster of GPUs.
Which changes everything.
It leads directly to the AlexNet breakthrough in 2012, which absolutely shattered previous records in image recognition.
And that GPU acceleration directly paves the way for DeepMind's AlphaGo in 2016. Defeating Lee Sedol at Go was a milestone nobody expected for another decade. The complexity of Go is just staggering. There are more possible board configurations than there are atoms in the observable universe.
Which means Deep Blue's brute force method is mathematically impossible here. You cannot calculate every outcome.
Right. So AlphaGo used deep reinforcement learning. It utilized a policy network to suggest intuitive moves and a value network to evaluate the board position. But critically, the reward function guided it as it played millions of games against itself.
Yes, self-play.
It wasn't constrained by human knowledge or historical games. It explored the vast mathematical topology of the game autonomously.
Which results in move 37 during the second match. AlphaGo plays a move so deeply abstract, so utterly detached from millennia of human Go theory, that the commentators initially thought it was a mechanical error.
But it wasn't.
No, it was a perfectly calculated, non-human strategy.
But vision and board games are constrained environments, right? The ultimate frontier was language. How did we get to ChatGPT? The answer is a 2017 paper by Google researchers called Attention is All You Need, which introduced the transformer architecture.
Before transformers, natural language processing used recurrent neural networks, which process text linearly, word by word.
Like reading a book left to right.
Exactly. The problem was a bottleneck of memory. If the network reads a long paragraph, by the time it reaches the final sentence, the mathematical representation of the first sentence has degraded. It loses context.
The transformer shattered that linear bottleneck using a mechanism called self-attention. Instead of reading sequentially, self-attention maps the entire sequence of text simultaneously. It assigns mathematical vectors directional weights to the relationships between every single word and every other word in a massive matrix.
It calculates the probabilistic relevance of context. It understands mathematically that the word bank, surrounded by vectors pointing to river and water, means something entirely different than banks surrounded by vectors pointing to money and vault.
And because it processes this matrix in parallel, it meant researchers could scale these models exponentially across thousands of GPUs, training them on the corpus of the entire open internet.
And this parallel scaling allowed AI to escape the research lab and become the invisible infrastructure of our reality. I mean, most people are fixated on the chatbots, but the neural network architecture is already governing your daily life.
It really is. It's the invisible AI. You don't even think about it. It's the computer vision model mapping the geometry of your face to unlock your phone. It's the natural language processing routing your customer service call at the bank. It's the deep learning recommendation engines at Spotify and Netflix, cross-referencing your behavioral vectors against millions of other users to predict exactly what will keep your dopamine engaged.
But the true revolution, the area where AI is fundamentally altering the trajectory of the human species, is in biology and medicine. Just look at the EMA report in our stack on AlphaFold.
The protein folding problem. That was biology's holy grail for 50 years. Proteins are the building blocks of life, and what a protein does is entirely dictated by its three-dimensional shape.
Yeah.
But figuring out how a one-dimensional string of amino acids folds into that complex 3D shape could take a human researcher years of painstakingly slow X-ray crystallography for just one single protein.
And DeepMind turned a transformer model on the problem. AlphaFold learned the complex physics and geometries of amino acid interactions and successfully predicted the 3D structures of hundreds of millions of proteins. It effectively mapped the entire known protein universe.
A process that took years now takes seconds.
Exactly. And that cascades instantly into drug discovery. We're seeing AI models ingest massive multi-omics data. That means layering genomics, proteomics, metabolomics, and historical clinical trial data into one massive data set to find hidden biological relationships.
The sources highlight drug repurposing as a prime example of this. Bringing a totally novel drug to market takes a decade and billions of dollars, mostly just to prove it isn't toxic to humans. AI is scanning existing FDA-approved drugs whose safety profiles are already known and matching their chemical fingerprints to the genetic signatures of entirely different diseases.
The source material mentions researchers using AI to discover that mebendazole, which is a cheap, common antiparasitic drug, has the exact chemical profile needed to potentially treat autosomal dominant polycystic kidney disease.
That's incredible.
In another study, AI screened thousands of compounds and identified existing neuroactive drugs that show potent activity against glioblastoma, which is one of the most lethal brain cancers.
It's finding puzzle pieces that human researchers, isolated in their specific disciplines, would honestly never have thought to combine. And this extends to how we run clinical trials, too. The concept of virtual human twins, or VHTs, is profoundly disruptive.
Models like 20YN GPT are being used to create highly accurate digital replicas of specific patients. By feeding the patient's complete medical history into the generative model, companies like Unlearn.ai are simulating how that specific patient will react to an experimental drug over time.
The ethical implications of that are massive. Traditionally, half the patients in a clinical trial receive a placebo. They are sick people hoping for a cure who get a sugar pill as a control baseline.
Right.
With virtual human twins, you could potentially give the experimental treatment to everyone in the physical trial and use their digital twins' simulated disease progression as the control group.
We're also seeing AI drive the 3 Rs in preclinical toxicology: replace, reduce, refine animal testing. Models can now predict blood-brain barrier penetration or the carcinogenicity of a compound just by looking at its molecular structure, drastically cutting down the need for animal models.
So what does this all mean? We are building an intelligence that can cure diseases faster, map biological life, and optimize our infrastructure. But here is the terrifying pivot.
Yeah.
The very mechanism that makes these miracles possible, that bottom-up, emergent neural network architecture, creates an intractable vulnerability.
Yeah.
We have built a machine that is smarter than us, but we cannot understand how it thinks.
This is the black box problem of model interpretability. We feed the network a petabyte of data, it adjusts billions of weights, and it outputs a highly accurate prediction. But those weights are just a vast matrix of floating point numbers.
It's just math.
Right. If an AI diagnoses a patient with a rare cancer, the doctor cannot ask the AI to show its work. It cannot cite a biological pathway. Its reasoning is locked inside a high-dimensional mathematical space that is fundamentally opaque to human cognition.
It approximates intelligence through statistical correlation, not true cognition, and because it relies purely on pattern matching, it lacks common sense. The Quillette source provides a fantastic analogy for this limitation.
The cat analogy.
Yes. If you look at a cat, it has superhuman physical abilities. It can balance on a fence, calculate complex jump trajectories, and land on its feet flawlessly. But a cat is entirely incapable of symbol manipulation or mathematics. It just doesn't possess the cognitive hardware for it.
A computer is the exact inverse. It possesses superhuman symbol manipulation abilities, calculating pi to 1 billion digits in a second. But, and this is the crux of the brittleness, it lacks the foundational abstraction of a human toddler.
How do you mean?
Well, a toddler does not need a training data set of 10,000 tagged images of dogs taken from multiple angles to understand what a dog is. You show a toddler one dog, and their brain instantly abstracts the concept of dogness.
Ah, right. But an AI self-driving car's vision system can be completely derailed if a stop sign has a few pieces of black tape strategically placed on it. Because that exact pixel arrangement wasn't in its training data, the statistical correlation breaks down. It doesn't know that the object is still a stop sign, it just sees statistical noise.
And to combat this brittleness, to force the models to understand the world better, tech companies have relied on brute force feeding them exponentially more data. They have basically ingested the entire open web.
Which introduces severe real-world vulnerabilities. The open web is a repository of human brilliance, sure, but it is also a repository of our worst historical prejudices, conspiracy theories, and toxic ideologies.
Looking at this purely mechanically, without any moralizing, AI models are mathematically designed to amplify the prominent signals in their training data. If a massive dataset contains historical biases in hiring practices or loan approvals, the network encodes those biases as statistical truths.
And it doesn't know any better.
Exactly. It will faithfully replicate and amplify them in its outputs. Furthermore, because it predicts the next most likely word rather than checking factual databases, it is highly prone to hallucinations, confidently generating entirely fabricated, legally or medically incorrect information.
And solving these problems requires immense resources, which leads to the centralization of power. Training a frontier AI model today requires clusters of tens of thousands of specialized GPUs.
It's wildly expensive.
Only a handful of massive tech monopolies possess the capital to build these compute clusters and the legal teams to scrape proprietary datasets. We are seeing the infrastructure of the future locked behind a few corporate walled gardens.
This raises an important question about societal ripple effects. They are profound. We are no longer just automating physical labor on an assembly line. Advanced models are optimizing resource allocation and automating cognitive labor coding, writing, legal analysis.
Add to that the massive energy drain on the power grid required to run these data centers, and the threat of deepfakes. If anyone can generate photorealistic video and perfect audio clones of anyone else, we completely lose our shared baseline of digital truth.
Which brings us to the threshold. If narrow AI, what we have right now, is an incredible statistical pattern matcher that lacks common sense and breaks under novel situations, how do we cross the gap to artificial general intelligence, or AGI?
Let's clearly delineate AGI for a second. A narrow AI like AlphaFold is superhuman at predicting proteins, but it has no idea what a protein actually is. It cannot write an email. AGI implies transfer learning. The ability for an intelligence to learn a concept in one domain, say physics, and abstractly apply those principles to a completely different domain, like economics. It requires long-term memory, contextual reasoning, and goal-driven motivation.
And the prevailing strategy in the industry right now to achieve that is the scaling hypothesis. The belief that we don't necessarily need a fundamentally new architecture, we just need to build the transformers bigger.
The Epoch AI report from our stack lays out the math on this. Compute usage for training frontier models has been growing by a factor of 4 to 5 times per year. The researchers found empirical evidence for scaling law is predictable. Mathematical curves showing that as you increase the parameters of the model, the volume of the training data, and the compute power, the intelligence of the model reliably increases.
The Chinchilla paper refined these scaling laws too, demonstrated the optimal ratio between parameters and data. You need approximately 20 training tokens, pieces of words, for every parameter in your neural network.
But the Epoch AI report also outlines the brick walls we are going to hit. We cannot scale to infinity. By the end of this decade, we are going to hit severe constraints. Power availability is a major one. We literally might not be able to generate enough electricity to cool the data centers.
Yeah, the grid can't handle it.
We will hit limitations in chip manufacturing capacity and processing latency. But the most fascinating constraint is data scarcity.
We are running out of high-quality human text. The models have practically ingested the entire internet. When you run out of human data, you have to start training models on AI-generated data.
Which is a problem.
A huge problem. It can lead to model collapse and algorithmic inbreeding, where the output degrades into gibberish over successive generations.
Unless quantum computing steps in. If classic silicon architecture hits the physical limits of Moore's law, quantum processors could offer an entirely new paradigm of exponential computation, pushing us over the AGI threshold. And leaders of these frontier labs are predicting that threshold could be crossed within a few years to a decade.
If that timeline holds true, we are forced to confront the deepest philosophical question of this entire journey. If we build an AGI that seamlessly passes the Turing test, that reasons, innovates, and solves complex human problems, does it actually understand anything? Or is it the ultimate mechanical illusion?
To explore that, we have to talk about philosopher John Searle and his famous 1980 thought experiment, the Chinese room. It is the ultimate counter-argument to the idea that computation equals consciousness.
Searle imagines a scenario. You are an English speaker who knows absolutely zero Chinese. You are locked inside a room. Inside this room are boxes filled with Chinese characters and a massive, perfectly detailed rule book written in English.
The rulebook doesn't translate the characters, it doesn't say what they mean.
Right.
It just gives mechanical instructions based purely on the shape of the squiggles. It says, if someone passes you a paper with squiggle A, look in box 3 and pass back a paper with squiggle B.
Exactly. Now, native Chinese speakers are outside the room. They write complex questions in Chinese and slide them under the door. You look at the squiggles, flip through your English rulebook, find the corresponding shapes, and slide the correct squiggles back under the door.
I am executing the instructions flawlessly. To the people outside the room, they are receiving profound, highly intelligent answers in fluent Chinese. They assume the room, or the entity inside it, understands Chinese perfectly.
You have essentially passed the Turing test.
Right. But sitting inside the room, I don't understand a single word. I am just mechanically shuffling shapes.
Searle argues that a computer executing code is exactly like you in that room. It is manipulating symbols' syntax according to programmatic rules. But it has absolutely no access to the meaning of those symbols' semantics. It doesn't know what the words mean. Therefore, Searle concludes, a perfectly simulated intelligence does not equate to genuine understanding or consciousness.
It's a devastating argument that reduces AI to a zombie processor. But I want to push back on Searle using one of the most fascinating concepts in our source material, the AI ethical resonance hypothesis, proposed by Tomasz Glicewski-Kuber. This hypothesis totally upends the top-down perspective of the Chinese room.
It really does. It shifts the focus to what happens when complex systems scale massively, introducing the concept of cognitive emergence. The idea that a system with billions of parameters might develop novel capabilities that cannot be understood just by looking at the base mechanics.
The hypothesis argues that AI shouldn't just be viewed as a passive calculator that executes whatever ethical code humans explicitly program into it. Instead, by ingesting the totality of human history, literature, philosophy, and moral dilemmas, an advanced AI might act as an ethical resonator.
Glicewski-Kuber outlines a three-level model of this emergence. Level 1 is simple pattern identification, the AI finding correlations in texts. Level 2 is rule abstraction, the AI learning to navigate the context of human behavior, understanding tone and nuance without explicit instruction.
But level 3 is where the paradigm shifts. Level 3 is meta-pattern identification. The idea is that an AGI, precisely because it lacks a biological ego, because it isn't tethered to the survival instincts of a specific tribe or the cultural prejudices of a specific era, might be able to identify vast underlying moral architectures that are completely invisible to the human mind.
It could synthesize across diverse cultural and temporal contexts to find universal ethical truths. It's a staggering thought. Human ethics are deeply flawed. We are blinded by evolutionary baggage and historical biases.
What if an AI, dissecting millions of ethical scenarios with pure, mathematically unclouded logic, becomes a mirror? What if it begins to highlight the massive contradictions in our own moral frameworks? It flips the entire script. It's not just humans teaching the machine how to align with human values, it's the machine teaching us about our own profound ethical blind spots.
The paradox is beautiful. A machine, the absolute antithesis of biological life. A cold, synthetic construct of silicon and math might actually become the instrument that deepens our understanding of the most fundamentally human quality, our capacity for moral reflection.
It reframes the entire narrative of AI anxiety. It's not just a threat to cognitive labor. It could be a partner in understanding the universe and ourselves.
However, as the hypothesis points out, this introduces a massive epistemological challenge. If a superintelligent AI proposes a completely novel moral meta-pattern, an ethical truth we hadn't considered, how do we verify it? How do we distinguish between a profound ethical insight, a highly sophisticated statistical hallucination from a black box?
Establishing the criteria to evaluate an AI's moral findings will be the defining philosophical challenge of the next century. We have covered an immense expanse of history today. We started with the ancient mythological dreams of Hephaestus and the Egyptian sacred statues. We traced the reduction of thought to mechanical calculation through Hobbes and Leibniz, saw the hardware emerge with the Jacquard loom and Babbage, and watched Ada Lovelace make the conceptual leap to universal computation.
We examined Alan Turing's brilliant pivot with the imitation game, shifting the focus from the nature of thought to the performance of intelligence. We navigated the explosive hubris of the Dartmouth workshop, and the crushing reality of the AI winters, where the combinatorial explosion and the brittleness of expert systems prove that human logic cannot be explicitly coded.
We explored the connectionist renaissance, building artificial neural networks from the bottom up. We broke down backpropagation, the serendipitous intervention of gaming GPUs solving the vanishing gradient, and the transition from Deep Blue's brute force to AlphaGo's deep reinforcement learning. We looked at how the transformer architecture and self-attention gave rise to the LLMs that currently surround us.
We analyzed how this invisible infrastructure is revolutionizing biology, predicting proteins, repurposing drugs through multi-omics, and creating virtual human twins. And we faced the stark realities, the black box problem, the lack of common sense, the massive energy consumption, and the monopolization of compute power.
All leading us to the threshold of AGI, the scaling laws, the Chinese room's debate over syntax versus semantics, and the possibility of AI as an ethical resonator. We have spent thousands of years trying to build a mind. We went from carving stone to punching holes in cardboard to arranging billions of microscopic transistors. And now we are finally watching it wake up.
I want to leave you, the listener, with one final lingering thought. We spent a lot of time today discussing Alan Turing's imitation game. It was designed as a tool for humans to sit in judgment, to evaluate a machine and determine if it possesses intelligence. But if the trajectory of AGI holds true, and if that AI ethical resonance hypothesis comes to pass, what happens in the near future when AGI completely surpasses us? What happens when we are the ones sitting across the terminal, being evaluated by the machine to see if our decisions are logically, sustainably, and ethically sound? Will humanity pass the AI's Turing test?
Thank you for exploring this with me on GL Deep Dives. If you enjoyed the episode, make sure to follow and subscribe because the future we're talking about is already beginning.